here this morning. And first of all, I'm really excited to be back at IPTCom because, as Carol was saying, this is the 12th edition, and I was actually there for the first two. So I was there in New York and Heidelberg, I remember. And then we kept on publishing things here, but usually it's Simon that is lucky enough to come here and present. This time, it turned out it would be me, so I'm really happy to be back. And I'll just say a few words about me. I got my PhD at the University of Napoli a couple of years ago, and I'm currently the chairman and one of the co-founders of a small company based in the south of Italy that is called Miteco, or Mitico as it was supposed to be called. And I'm mostly known in the WebRTC community for being the main author of Janus, which is a WebRTC server that I briefly touched during the course of this presentation, even though I really don't want it to be very much Janus specific. I'd like it to be mostly some guidelines that you may want to take advantage of for your own projects instead. And there you can find some links if you want to contact me or maybe get some more information about other things I've been talking about in these past few years. And so the real topic that we wanted to address here was basically vulnerabilities in RTC communication. So you may be aware that Project Zero actually identified some key issues in RTC communications a few months ago. So basically what they did was they started focusing on popular video conferencing applications, usually applications like FaceTime, WhatsApp, and others, to basically try and identify some potential vehicles of attack or issues that may actually cause problems, or even more than a few problems. And they focused a lot on basically using fuzzing, or mostly end-to-end and RTP testing kind of functionality, in order to try and verify if these applications were actually vulnerable as they thought that they were, using randomized input and things like this, and most of the times also writing ad hoc components for the job. And eventually it turned out that these applications did have some issues, and probably not surprisingly for a few people, a bit surprising for us, WebRTC was suffering from this as well. And then when I mean WebRTC, I mostly mean the open source libWebRTC application framework that almost all of the browsers out there use today. And there were basically some issues that were eventually solved by Google by fixing it. But of course, WebRTC is not just that. There are several other applications that make use of WebRTC every day. And in fact, Philip Panke, who is another very well-known expert in the WebRTC community, basically raised some sort of wake-up call for all of the people involved. He basically wrote a blog post on WebRTC hacks that I encourage you to visit if you're not aware of it. It's a really interesting source of information for WebRTC. And he showed how easy it was to basically just crash an application by just sending it broken information, basically. And funnily enough, I mean, not very funny for me, but funnily enough, he used Janus as a way to actually prove this. So he basically showed how you could use some weird-looking RTCP packets to just bring the whole framework down, which of course was very problematic for us, and we wanted to solve it. And so the first thing that you have to ask yourself when it comes to WebRTC is what can actually cause trouble when it comes to this. And there are actually several, let's say, attack vectors that we can see in WebRTC, and signaling is usually not one of those, because for instance in the past you could have SIP heavily tested and validated in order to make sure that a weird header wouldn't crash your old SIP server. With WebRTC, this is usually not the case, because WebRTC, as you know, is signaling agnostic. So you should still take care of signaling and make sure that everything is properly done there, but it's not a problem in the WebRTC specification per se. But there are actually a lot of other protocols that you should be worried about instead, because all of these protocols that you see over there are binary protocols that use information that uses some specific boundaries and so on, and so protocols that you have to be very careful about when you handle them. So anything that relates to ICE, to the DTLSS RTP exchange, RTP and RTCP packets in the secure version as well. Data channels are based on SCTP, and so that's another protocol that you need to be very worried about. And of course, it doesn't just stop there, because the moment that we start involving RTP in the picture, then you have to worry about codec-specific payloads as well, because you may want to do simulcast, you may want to investigate if a frame is a key frame or not, and a few other things. All of these actually involve having a look inside of the payload of the RTP packet, which can introduce problems of its own. And so fuzzing is of course very helpful in this case, because it helps you basically introduce some randomized information in the picture to see whether or not your parser, your software is actually able to to verify that this packet is not actually what it's supposed to be, so that you don't, for instance, go reading where you're not supposed to do, and so possibly going to read behind the boundaries of the packet itself. And basically this is a very simplified description of how the typical workflow of a fuzzing framework works, but in general what you do is you inject some random information in your application, usually based on a specific corpus, because you want the packets to look like the real thing, but it's weird enough and, let's say, different enough to not actually be the real thing. So for instance, an RTCP packet with some weird data there that actually corrupts it. Of course, just showing random information is helpful as well, but most of the times you want to be sure that the parser is robust enough to actually be able to handle some slight variations as well. You basically pass the same input over and over again, maybe slightly mutated, in order to figure out that things are actually supposed to be working. You monitor how your parser is working, possibly using sanitizer tools and so on. On coverage-based fuzz testers, you also update the coverage. So basically you verify if all of the parts of your code are actually being solicited by this input and not just some very specific parts of the code and other parts that are instead never covered at all. And you basically repeat this loop until it, hopefully or hopefully not, it depends on what you want to do, until it crashes. And so when it does, you basically have a way to actually investigate what was happening. And repeatability is, of course, very important and can be ensured. And this is what led us then to this. So as I was saying, I'm the main author of Janus, which is an open source WebRTC server implementation. And you can find some links there if you're interested. And basically, it has a modular architecture. So it has all the WebRTC stuff is part of the core, and everything else, which means signaling protocols, how we handle media, if you want to do an SFU, an auto mixer, and so on, this is all part of a modular plugin architecture as well. And interestingly enough, this is a fun fact, this was actually inspired by some work that I did a few years ago in the media control framework. So Eric is there to attest the efforts that I made in that. And so all the work I did there actually helped a lot in creating all of this. And the reason why I'm introducing all of this is to explain basically the effort that we had to do in order to evaluate what we had to do in order to make sure that where we had to put our hands for the fuzzing part. So for most of the protocols, we were lucky enough that we are currently using some well-known libraries. So for instance, libnice for all the I stuff, for all the DLS exchanges, we use OpenSSL and so on and so forth. And all of these libraries are actually fuzz tested quite extensively on their own, which means that we didn't have to worry much about that. We are quite sure that stump packets are never going to cause trouble. We are not going to handle them ourselves. The library is, and so we are, let's say, confident enough that there is no problem there. Signaling may be a bit of a problem, but we use a lot of dependencies there as well. So even if there is some things that need to be done, for instance, making sure that a WebSocket connection doesn't crash our server, it probably needs to be done in the library that actually implements the WebSocket protocol rather than Janus itself. So we really wanted to focus on what we really have some control on, which means all of the custom code that we added to implement RTCP parsing, RTP processing, and so on. And so actually RTCP was the first packet that we started from, mostly because it's very problematic in how it's written, and it leads easily to crashes. And basically to do this, we basically used libfuzzer, which is a quite common framework that is part of the LLVM project and is actually used by many of the projects that I already mentioned before. So for instance, OpenSSL, SQLite, FFmpeg, they are all using libfuzzer in order to make sure that they are not vulnerable to this kind of attacks. And when you want to use libfuzzer in your project, it's important that it can be compiled with clang. So this is one of the things that we had to do. It works in process, which means that you typically build a separate version, or you typically integrate in your own development process, because it needs to work with the actual functions that you are working with. It uses a specific function, as we'll see, to inject the problematic, let's say the problematic input, and then it basically monitors what this function is doing in order to verify how this all works. And just to give you a quick idea, this is basically the kind of loop that happens when you integrate this process into your workflow. This is how, from a very high-level perspective, this works. So you have a function that has to be called like this and has to implement that signature. And basically you see that basically this function just gets some raw data, and you know how much data you just received, and then you do everything in there. So you have to do everything in this function. You have to treat that data as constant, which means that you must not touch that data. If you want to modify it somehow, you have to make a copy of that. You make sure that you clean up for yourself, that you don't introduce any leaks, because otherwise the sanitizer will intercept it and treat it like an issue that you need to solve. But in principle, that's what you need to do. So this function will be called over and over anytime you return from it. So anytime you return, new data will be passed to it, new data will be processed, and so on and so forth. And so, as I said, you need to compile it with Clang. In this case, for instance, we are enabling a couple of sanitizers to be able to validate it. And eventually, as soon as it is compiled, you just run it, you pass a folder where you have some valid packets that you want to start messing with. So, for instance, in the case of RTCP, some valid RTCP packets, then the fuzzer will start messing with in order to introduce variations. And again, you can repeat until it crashes. When it does, you can just relaunch the same application, passing as the argument the actual packet that crashed the whole thing, because libfuzzer will do that. As soon as it crashes, it will generate a file with the content of the message that was actually causing the issue. And for instance, you can pass it to a debugger in order to evaluate whether or not what the issue needed to be fixed. Basically, it's simple enough in its process, but it took us a bit of time in order to actually do the whole integration. But the nice thing is that it's actually quite easy to basically get to a problem, use this, take this file, pass it again to the application, and evaluate what the cause of the issue was. So, for instance, reading out of the boundaries or things like this. And again, as we said, we needed to make sure that we could use Clang for the purpose, because Clang is not GCC. It has some differences. It's also a bit more strict in some aspects. And so we did get some useful warnings when adding support for Clang as well, because it raised some flags that we needed to do. But in general, that process was easy enough. Then we decided to start with RTCP, as we said, mostly because of the nature of RTCP itself. So, and basically we had to start working, and because it has a lot of compound packets, a lot of length variables to be worried about. So it's a problematic protocol, let's say it like that. Even though we also moved to RTP and partly SDP as well, but RTCP was the main focus here. And basically what we did was first create that fuzzing function as we introduced it before, specializing it for RTCP instead. Write a lot of helper scripts to build the fuzzer in order to integrate it into our workflow, and then also some scripts to basically run it into a more or less automated fashion. And it eventually landed up in a pull request that since we merged, because this is from a few months ago, but you can find some information there if you're interested in exactly what we did to do this. And this is a very simplified overview of how the libfuzzer function works in our case. So for instance, we do some checks. If a packet is lower than 8 bytes, it's not RTCP at all. If it's higher than the MTU, it probably never came from the internet at all, so we really don't bother. We have some functions to validate if it's actually RTCP, which simplifies also a couple of things, and then some functions to crawl it to see if it's a sender report, a receiver report, if it's an ACK. Basically, you try and stress test with all of the different RTCP kind of packets and see, and hopefully it never crashes when you do. I was mentioning code coverage, which is actually quite important, that libfuzzer gives this basically out of the box for free. And it's important because it gives you an idea of how many times the fuzzer went through each of the lines in your code. So in this case, for instance, we never went through the point that checks if a packet is too small, because we actually have a check that actually never involves those functions in the first place. But in general, you want to make sure that all your code is actually triggered. Otherwise, you may have some blind spots that are actually not covered and may actually present issues. Core profiles are important. So I was mentioning valid RTCP packets, for instance, in this case, to start from. And there are some packets that libWebRTC provides out of the box, but we are actually contributing some of our own. Other projects like Media Soup by Iñaki Bascastillo is providing others. And in fact, we created together an open GitHub project to actually host more files. So if you have packets that are known to cause problems to parsers, by all means contribute them there so that other people can get them and try to evaluate if it crashes for them as well. The last part of our effort was also integrating all of these in OSS fuzz, because of course fuzzing is only helpful when you do it repeatedly over time and so on and so on and so on, because the fact that it didn't crash in 10 hours doesn't mean it won't crash in 20 hours. So putting it into a framework that does nothing but this, basically just hammering it over and over and over all the time, is actually very helpful, which is what OSS Fuzz is. It's a project by Google that basically does fuzzing as a service. So you create a few Docker projects to basically show how you can compile the whole thing. You provide a couple of scripts, and then it's part of the project if they accept your pull request. And we actually did that, so it's part of this. And it's quite helpful because anytime something happens, they notify you via mail. You can check what happened. They also don't just use libfuzzer, but they also use AFL, for instance, as part of their process. So it's quite helpful and a very easy way to integrate all of these. And of course, I went really fast with these just to give you a very quick overview. But if you want to know a bit more about how this all works, a few months ago we actually wrote, not me, Alessandro Toppi, who is the guy that actually worked a lot on these aspects, wrote an extensive blog post on all of the aspects that I briefly touched here. So if you are interested in seeing how you can do pretty much the same thing for your project, this is definitely a good starting point because it goes into details about all the CLANs, complexities, all that you have to be aware of in terms of creating your function, the sanitizer process. Basically, all those minor details that you may not be aware of that actually do need some processing. And again, as I was saying, we started with RTCP. We did a lot of work for the RTP as well, and we did some part with SDP as well. But the SDP fuzzing actually could take some additional work because it's actually text-based rather than binary-based as the other protocols, and so may benefit from some structure awareness that we are not putting in there for the moment. And I mean, we're not doing anything in plugins as well. So we are going to do something like this. We want to expand the corpora files, that project that I was showing you before. And as I was mentioning, libfuzzer is not the only options. There are other options. One of those is actually by Dr. Alex, who is sitting over there. They have a modified version of a browser that actually generates malicious RTP and RTCP packets. So all you have to do is take that browser, point it to the website of your application, and see it die in flames, basically. So it's a very useful and effective way to do fuzzing without actually having to touch the code. And it's part of their Kite framework, so it's definitely something to investigate. And really, that's all. So I don't know if we have time for questions, but I thank you for your attention.